Hello and welcome back to Mrs. Ogram's Maths. Today we are doing a word solution video for differentiation. This is from the external that was done in 2022. I'm just catching up on a few work solutions that I haven't got around to doing. So this is the 22 paper for differentiation. Okay, question 1a. We are differentiating this function here, which is a chain rule because we have a function inside of another function. All right, so differentiate the outside, and that becomes 2 to the power of 1. Well, we don't need to write the power of 1. So leave the inside alone, and now times it by the derivative of the inside, which is 1 over x. You can, of course, simplify that, but you don't need to, and I would recommend on achieved questions you don't try to simplify because you could make mistakes. Okay, for part B, we're finding the x values of any stationary points on this function, so we need to differentiate it and set it equal to 0. So f dash of x, we're using the quotient rule here, so we need v du by dx. So v is x, du by dx is the derivative of the top, which actually is just 2x, that was easy, minus u dv by dx. So the top times the derivative of the bottom, which is just 1, all over v squared. Then we carry that on, and actually at this point I'm going to go straight to setting it equal to 0, because that's what we need for stationary points. Because then if we think about bringing the x squared up to times by 0, it's going to get rid of that bottom for us. So we're just left with the numerator, 2x squared minus x squared plus 1 equals 0. So x squared plus 1 is equal to 0. Oh, hold on, I've messed up my negatives. That's a minus 1 there and a minus there. So that's because the minus just here gets times by the plus 1 there when we expand those brackets. So x squared is equal to 1, so x is equal to plus or minus 1. All right, for part C, we are looking at the equation of a normal to a curve. First thing I'm going to do is write this in powers form for the equation of the curve. So that's to the power of a half, which means that the derivative is a half x plus 2 to the minus a half. Now we want the, we can see that the point at which we're finding the gradient is when x is 0. So when x is 0, then the gradient is equal to a half plus, times 0 plus 2 to the minus a half. Or in other words, it is 1 over 2 root 2. Now that gives us the gradient of the tangent. We want the gradient of the normal. So the gradient of the normal is the negative reciprocal, so we flip it over and times it by a minus 1. So we get the gradient of the normal is minus 2 root 2. We want the equation of the normal so that we can then work out p. So y minus y1 equals mx minus x1. So this point here that we've got, that is when x is 0. And the y value, if we go back to our original function just here, is going to be 0 plus 2 makes 2, obviously, and then square root it, so it's 0 root 2. So popping in our y value just over here, we get y minus root 2 is equal to m, which is minus 2 root 2, x minus 0. And then just rearranging that, we've got y equals minus 2 root 2 x plus root 2. Now to find the value of p here, that happens when y is 0. So at p y equals 0, so minus 2 root 2 times x plus root 2 equals 0, which gives us that x is equal to root 2 over 2 root 2, so x equals a half, and p is a half 0. Part D, we've got parametric equations. So dx by dt is equal to 3. dy by dt is equal to 3 minus, if we're differentiating log, then it goes 1 over, so that's 3t minus 1. And then because we have something inside of the log here, then we have to multiply by the derivative of that, which is 3. Oops, wrong pen, hold on. There we go. So then dy by dx equals dy by dt times dt by dy. So dy by dt is going to be 3 minus 3 over 3t minus 1, and times it by 1 over 3. That simplifies to 1 minus 1 over 3t minus 1. Then back to the question, find the coordinates for any points where the tangent to the curve has a gradient of a half. So we're setting that gradient to be equal to a half now. So if that, in fact, I'll just switch colour so you can see the next step. So that we're setting equal to a half. Okay, so I'm going to bring the half over to the left. So 1 minus a half becomes a half, and take the fraction part over to the right, so it becomes positive, like so. So 3t minus 1 equals 2. So 2 will be, t will be 2 plus 1 is 3, and then it gets divided by 3. So t is 1. Now it's very tempting to finish there feeling like you've got to an answer, but we're not quite there because we need the xy coordinates, and at the moment we only have the value of t. So we go back up to how to work out x and how to work out y using that t value. Okay, so I'm going to need to just shrink this a little bit. There we go. When t is 1, x equals 5 and y equals 3 minus natural log, and all I'm doing here is subbing into these equations up at the top here. So when t is 1, we've got 3 on the first term minus log of 3 minus 1, so log 2. So the point is when we have the coordinates 5 and 3 minus log 2. Now on this bit here, you can leave it as 3 minus log 2, or you can do it as a decimal. Either one of those will be marked as correct. All right, now for our first excellence of the paper, we want to prove that this equation has no points of inflection. Points of inflection, we need the second derivative, so let's get to there first. So dy by dx, to differentiate this thing, we're going to, well, e itself doesn't change, but we have chain rule because we have a function inside of the power. So we will multiply by the derivative of the power, which is 2xp, and then e to the p x squared. Then the second derivative is going to involve the the product rule, because we have one piece just here being multiplied by another piece just here. So those are the two bits that we are differentiating and multiplying together. So differentiate the first one with respect to x, and we get 2p, times it by the original of the second. Then leave the first one alone and times it by the derivative of the second, like so. Now for points of inflection, we're looking for when that second derivative equals 0. And now we need to solve this. Okay, so I'm going to start by factorising out e to the px squared. I can see that's everywhere. So is 2p. Okay, so then from the first term we get a 1, and then from this second piece here, we've factorised out this bit. We've factorised out a 2 and we factorised out a p, which means that what we're left with is 2x squared p. And that has to equal 0. Right, now let's take the pieces here. 2p can't be 0 because p is a positive real constant. Then this bit can't be 0 because e to the power of anything is always going to be positive. That's part of the nature of the e function. So that bit can't be 0, which leaves us with the last piece carrying on with 1 plus 2x squared p is equal to 0. So now rearranging for x, we would have 2x squared equals minus 1 over p. So x squared would be minus 1 over 2p. Now, since this is negative, we can't square root it, or rather, if we did, we would get complex roots, and this means that it does not have any real solutions. Right, back to some achieved questions for question 2, and we have a product rule with two pieces being multiplied together here in the blue and the yellow. So to differentiate this, we are going to do the first one differentiated, which is 5, times by the second one, then add on the first one left alone and times it by the derivative of the second one. Well, sine goes to cos, but we also have the 4 inside there, so we've got chain rule, that'll get times by 4, and then my preference is probably actually to write that as a 4 at the front, but you don't necessarily have to do that. For part B, we are going to find the derivative of this curve. We differentiate the outside, leave the inside alone, times it by the derivative of the inside, so a little bit of chain rule, and then working out when x equals 2, y will be 3,600 just by substituting 2 into this equation here. For part C, we have a little bit of kinematics. We've got the displacement, and we need to find the times when the object is stationary. Now, since we're in a differentiation paper, you can go ahead and assume that you need to differentiate this thing, which actually helps a little bit with this question because it's not so obvious to everybody what we're looking for. But for when the object is stationary, meaning it's not moving, then the speed will be equal to 0. So to get speed from distance, we differentiate. So if we differentiate this thing here, I'm going to use the product rule. You could also simplify this fraction, separate it into 2 separate terms. I'm going to go with product rule, but that also would equally work. Okay, so the first thing is to do v times du by dx. So the top derivative is 2t, minus u dv by dx, so top as it is, and times it by the derivative of the bottom, and then divide it by v squared. Now we're going to set that equal to 0 because we're finding out when the object is stationary. So now if we bring that up and times it, it's going to equal 0. So we're just left with the numerator equal to 0. Which means that simplifies like this. And we can factorize out 2t squared. And then we would get either t equals 0 or t squared equals 18. So we've got a solution there. It was stationary at the start, and we want to find the next solution. So t squared is equal to 18, which means that t is plus or minus the square root of 18. But in this case, a negative time wouldn't make any sense, so we just take the positive. So it'll be stationary at 4.24 seconds. Okay, so we've got this rectangle. We want to find the maximum possible area. I'm just going to write the equation on this so I can see it when we need to scroll down to actually write our solutions in. So if we want to maximize the area, we first need a formula for the area. So the x will be the base of this triangle, and the height will be the y value, which is 6e to the 1 minus 0.5. Oops, hang on, let me just start that again. 6e to the 1 minus 0.5x. Okay, so if we're maximizing, we differentiate this and set it equal to 0. So if we differentiate this, we have a product rule first of all. I'm going to rewrite that as 6x, like this. So we'll do 6e to the 1 minus 0.5x. So I've differentiated the 6x, left the e part alone, and then add on, leaving the 6x part alone, and then differentiate the e part, which is minus 0.5 e to the 1 minus 0.5x equals 0. Now if we factorize out 6e to the 1 minus 0.5, I'd set it equal to 0 because we're finding a maximum, remember. So this will be 1 plus, actually I can only take out 3 here. So this will be a 2 because my 6 here got times by 0.5. So that's, I'm going to have a 3 there. So if I take the 3 out, this will end up being plus, the minus actually makes it a negative. X is the only bit that's left there. So just to tidy up what I was doing, if we take this bit here, just to make it super clear what I did there. So 6x times 0.5 is going to be the negative 3x. And then when I take out the 3 and the e part over here, we're just left with the x. Just undo that just for completeness. All right, so that then equals 0. Now to make that equal 0, one of those pieces being times together needs to be 0, and it can't be this one, because e to the power of something can't equal 0. So therefore x equals 2. Now we got to make sure we don't stop there. We're not finding the x value when it happens. We actually need to find the maximum possible area. So moving on to the next step to finish this off, when x is 2, the area equals 6 times 2 e to the 1 minus 0.5 times 2. So we've got 6 times 2 e to the 1 minus 0.5 times 2 is just going to be 1. That's to the power of 0, so that makes it nice. So that gives us an area of 12. Okay, for part E, our excellence question, we have a tangent that runs through P, something like this. Carry on that axis that way, and we're told that it intersects the x and y axis at R and S, and we need to work out the length of it. I'm going to do that up to the right hand side here, just hoping that we can fit that onto one screen. So we're going to want to differentiate the equation of the curve so we can get the gradient of that line, then find the equation of the line to find the coordinates of these 2 points, then the distance between them. Right, so back to step 1. Here's the equation. We can't differentiate it yet in that form, so let's just do a bit of rearranging. So here we go. Y minus 5 equals the square root of the other side, so that'll be 4 square root of x minus 2, which actually I'm going to write in powers because here we go, because I know we're going to differentiate it a bit later. So y would be 4x minus 2 to the half plus 5. Now y dash, differentiating that, the half times the 4 because this is chain rule would be 2x minus 2 to the minus a half, we would times it by the derivative of the inside, but that's just 1. 5 when differentiated is 0. Okay, so there's our gradient, which we're told in the question that the gradient of that line is 1. So set this equal to 1, and we'll go through and solve it. All right, so this is 2 over the square root of x minus 2 is equal to 1. So the square root of x minus 2 will equal 2. X minus 2 is 4, x is 6. So at P, our x coordinate is 6. Now we need the y coordinate. Let's sub it back into y minus 5 squared equals 16. 6 minus 2. Okay, so that's going to be 6 minus 2 is 4. 4 times 16 is 64. So y, if we square root that, we are obviously going to get 8. And then add on the 5, and we get y is 13. So y minus y1, which is 13, is equal to m, the gradient, which is 1, x minus 6. So we're just finding the equation of the tangent line now. So y equals x, it'll be minus 6 plus 13, so that's plus 7, which means that our r coordinate is going to be, when y is 0, x will be minus 7, so this is 7, 0. And the s coordinate is equal to, when x is 0, then our y coordinate would be 7. So now we have this triangle. It's right-angled, so we can work out the length here of the hypotenuse. So finishing this off, rs is equal to the square root of, well, the x direction is 7, the y direction is 7. So this is the square root of 49 times 2, which is 7 root 2. Okay, question 3. First of all, rethink this as e to the 4x to the half. Now differentiating that is chain rule, so the e doesn't do anything, but we differentiate the inside, which would be 2x to the minus half, e to the 4x to the half. Okay, for question B, I'm just going to need to squidge this up a little bit to fit everything on. So we've got this function, and we need to work out some values. So the first one is find the values of x where f of x is not differentiable. That's anywhere that we have gaps. So that will be at x equals minus 4, where we have a hole in our function there. Then anywhere that we have kinks. So it's those two corners there. So minus 4, minus 1, 1. Now find the values for x for which the gradient is equal to 0. So that's stationary points and flat lines like this. So that will be x equals minus 3 and x is greater than 1. And finally, the value of the limit as x is approaching minus 4. So what's happening to our graph as we go towards, as we go towards minus 4. So here's the minus 4. What happens on the graph as we're going this way towards minus 4 and that way, and it's going towards the same value, and it is finite. It's a value of minus 3. So the limit is minus 3. Right, for part C, we have a bit of rate of change. We're told the volume can be calculated by this much. We've been given a constant rate here of the water being poured into the bowl. So I'm going to write that down first. And we do that by saying the volume is changing with respect to time at a rate of 20. What we want to find out is the rate at which the height of the water is changing. So that's the rate that we want, dH by dt. Now figure out how to make that from the rate that we've got. We can do dV by dt, the rate we've got. We would need to times it by dH. so that we introduce the dh that we want, and we need to divide by dv to get rid of the dv that we don't want. Okay, so dv by dh, let's start with that one. So this is the v formula here. We're going to differentiate it with respect to h. So the first term will become 3 pi h, because that h squared gets times by 2, and so the 2 here cancels. The second term that starts off as 3h pi will then differentiate to just 3 pi. Okay, then we have dh by dt. The thing that we wanted to work out will be dv by dt, which we know is 20, and then times it by dh by dv, which is 1 over this, because it's the other way around to what we want it to be. So now when x equals 3, we can sub it into this formula here to work out dh by dt. So popping a 3 in gives us 20 over 12 pi, which is 0.531, and then just check the units that we need in the question, which is to do with centimeters and seconds. So it'll be the height is changing in centimeters per second. Okay, part D, we want to find the x values for any stationary points from this function here. So first I'm going to rewrite that with the fraction in power form instead. Now differentiating each term, we get 9, the 2 goes away. This bit here, we're going to differentiate the outside, so it becomes -3, and then reduce the power by 1, and then times it by the derivative of the inside. Now we set that equal to 0 and continue through solving it. So we end up with this squared part here is equal to 1. So either that would be equal to 1, or it would be equal to -1, and we'll get a solution from each of those. So this one gives us x equals 2/3, and the second one gives us x equals 1. Now we work out the nature of the stationary points at those x values. So for that we need the second derivative. So looking back up here at this equation here, we need to differentiate that again. Now that's a chain rule. The 9 differentiates away here, but the -2 times the -9 makes the 18, and reduce the power by 1 to be -3. And then times 3 for the chain rule. So this becomes 18 times 3 is 54 over 3x minus 1 cubed. So when x is 2/3, then d2y dx squared is going to be 54 over, let's pop that in, 2 divided by 3, so 2/3. We're going to times it by 3 and take away 1, and then do it to the power of 3, which is still just going to be 1. So 54 over 1. It's greater than 0, therefore it's a minimum. And the other one, when x equals 0, d2y dx squared is going to be 54 over -1, which is less than 0, therefore it's a maximum. All right, part E. We've got Megan cycling from her home at H to school each day, and there's a point P where she rides along a path from her home to P at a constant speed. At P, she then cuts across the park and goes directly to school. When she's cutting across the park, her speed slows down to 6 kilometers per hour. I assume because she's then on grass. So then at what distance from her house should she cut across? So P can be anywhere along this section here when she chooses to cut across the grass. So where's the best time to do that so that she can be most efficient and make her traveling time a minimum? So let's start by calling that bit x, and then this bit 4 minus x. So h to p is x, and 4 minus x is what we have left, because the total from h to q was 4. To help with some notation here, I've just also said here that x is the distance from home to p and t is the travelling time. And the reason we're doing that is we want to minimize that traveling time. So we need an equation for that total traveling time. So the traveling time spent going from H to P, have a think about what we mean by speed. When we're saying speed is 10 kilometers per hour, it's the kilometers divided by the hours. So if we rearrange our speed time equation, time is distance over speed. So the distance is x and the speed is 10. Then we need the distance of PS, just here, and we can use Pythagoras to do that. So we get that the distance of PS is going to be this. Now I've skipped through that quite quickly just for the interests of time. We're just using Pythagoras on this triangle here, where that's a 2, that's a 4 minus x. That means we can work out the time that it takes to go from P to S, because we've got a distance. Then the speed that's done over that distance is 6. So the time taken will be that distance divided by 6. Now for the total time, that total equation will be the time spent on the first section plus the time spent on the second section. And the reason for getting this is we want to minimize this, so we want to find a stationary point of that. Now to find stationary points, we need to differentiate. So the first term will be 1/10. The second one, we have a chain rule. So we've got, went a bit fast there, the outside differentiated, leave the inside alone, then times it by the derivative of the inside. Now for the minimum, we need to set that equal to 0. So here's the equation set equal to 0. Solving that looks like this. So I've got all the steps written out for you here. We're going to move the 6 and the square root over to the right hand side. The 10 comes over here with the 5, turning into the 5, and just carrying on working through that equation. When we're at this side here, we're going to square both sides so that we can continue working it through. Now get down to solving this quadratic here, and we get 2x minus 5 equals 2x minus 11. And setting that equal to 0 means that x is equal to 5 over 2 or x is equal to 11 over 2. Now in terms of distance, that's 2.5k and 5.5k, but this 5.5 is not a valid solution because of the context of the question. It can't be more than 4k. Just take a quick squiz back up at this diagram here. It can't be 5.5 because the 4k hit there. So that distance from her home, she should then cut across the field when x is equal to 2.5k from her home. So just thinking back to what our solution means, here's the x, remember, so this is the distance, 2.5 is when she should shoot off. And that's 2022 done. If you are having a mooch around on my channel, check out the Merit a Day lives that I've been doing. They're very, very helpful in your lead up to practicing your exams. All right, see you next time.